I'm Mark Arenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 32. We say an n-digit number is pan-digital if it uses all of the digits from 1 up to n exactly once when written in base 10. For instance, the 5-digit number 15,234 is pan-digital, since it uses the digits from 1 to 5 exactly once each. You're going to want to get used to this definition going forward, because Project Euler really loves the word pan-digital. But for today, we're not looking at pan-digital numbers. Instead, we're looking at pan-digital products. Consider the product displayed here. 39 times 186 is 7,254. This product, when written out in full, contains 9 digits. In particular, it contains all of the digits from 1 to 9 once each. So it would be reasonable to call such a product expression pan-digital. The problem asks us to find the sum of every value which can be written as a pan-digital product using the digits from 1 to 9 exactly once each. Crucially, we're only interested in the set of product values, so if a single result value can be written as a pan-digital product in 2 or more different ways, we only want to count it once. Let's begin by discussing the magnitude of the number we're looking for. If I have 2 numbers, let's say capital N and capital M, where capital N has lowercase n digits and capital M has lowercase m digits, then how many digits does the product NM have? To answer that question, we first need to ask ourselves what it means for a number to have a certain number of digits. For today's problem, we're working exclusively in base 10, so I'll be assuming all of our exponential bases are 10. But anything we do today could be done in any positive integer base greater than 1. I said that capital N is a lowercase n digit number. The smallest lowercase n digit number is 10 to the power n minus 1. If lowercase n is 1, then this is 10 to the 0 power, which is 1. If lowercase n is 2, this is 10 to the first power, which is 10. If lowercase n is 3, this is 10 to the second power, or 100, and so on. On the opposite end, the smallest number with more digits than we want is the next power of 10, or 10 to the lowercase n. So when I say that capital N is a lowercase n digit number, what I mean is that capital N lies between 10 to the n minus 1 and 10 to the n, where the upper bound is strict. Now we can write the exact same thing for capital M. Every number I've mentioned so far is positive, and the nice thing about positive numbers is that when we multiply them, inequalities are preserved. So when we multiply capital N and capital M, we get a number that's between 10 to the power n plus m minus 2 and 10 to the power n plus m, where the upper bound is, again, strict. This tells us that the product nm must have at most n plus m digits and at least n plus m minus 2 plus 1 or n plus m minus 1 digits. Going back to our original problem, we want to write a multiplication statement n times m equals k, such that the total count of digits in n, m, and k is equal to 9. I claim that k, the product, must have at most 4 digits. To see this, suppose to the contrary that k has 5 digits. As we've just seen, to get a 5-digit number as a product, we need the total count of digits in the multiplicands to be 5 or 6. This means the total number of digits in the entire statement is either 10 or 11, which is too large. And naturally, if k has more than 5 digits, the problem will only be exacerbated. Thus, k has 4 digits or fewer. Beyond that, there's really no clever mathematics here. We can enumerate all of the potential products from 1 up to 10,000 exclusive and test all of their factors. Let's start today by writing a draft in Rust. I've mentioned Rust in passing several times, but to this date, we haven't actually written any code in it. Rust is, in many respects, a modern reinvention of all of the core ideas of C++ from the ground up, with the benefit of nearly 30 additional years of knowledge and experience in what works and what doesn't work in programming language design. Let's put that another way. In the 1980s, a team of very smart engineers got together, looked at C, and added a bunch of high-level programming features on top of it, such as classes, templates, and function overloading, to get what we call C++. More relevant for this discussion, however, they added safety features, such as automatic class destructors and copy constructors, which, when used correctly, decrease the chance of your program falling victim to use-after-free or similar memory corruption issues. Unfortunately, these engineers were hampered by the fact that they lived in the year 1985. The Turing machine was only 50 years old, Unix only 20, and the IBM personal computer had come out a mere 4 years ago. Computers were new, and the field of programming language theory was, likewise, very young. 30 years later, another team of very smart engineers got together, looked at C, and added a bunch of high-level programming features on top of it, this time creating Rust. But this time, they lived in the year 2012. The engineers who created Rust looked back at all the mistakes of the past, and had a chance to reinvent many things through a modern lens. At a surface level, Rust code strongly resembles C and C++ code. It uses braces for blocks, parentheses for function calls, and is not indentation sensitive like, for instance, Python is. But much of the historical baggage of languages like C++ and Java has been corrected. Most critically, Rust adheres strictly to a single ownership model. That means that at any given moment, a piece of data in memory is owned by exactly one source. That source could be a local variable in a function, a captured variable in a closure, or a field on a struct. When that source is freed, for instance when the enclosing function is ended, then the variable will be freed. C++ does the same thing for local variables, but the crucial difference is in the handling of pointers. C++ has a smart pointer system. Modern C++ developers are strongly encouraged to favor smart pointers, such as unique pointer or shared pointer, over the use of raw pointers, but regrettably, it's not uncommon to see the use of the latter in C++ code even today. Even freshman-level university courses often still teach C++ in terms of raw pointers, even though much better alternatives exist. On the flip side, Rust points its developers in the correct direction to begin with. Smart pointers such as box, RC, and references are presented as the only option in all of the tutorials, and raw pointers are locked behind the scary keyword unsafe. The net result is that the vast majority of Rust code is memory safe, with possibly only a few small portions being explicitly marked unsafe, whereas the vast majority of C++ code is pointer manipulation, with perhaps some verifiably safe oases sprinkled throughout. Similarly, Rust corrects the so-called billion-dollar mistake of null pointers. All of the smart pointer types I mentioned in Rust are non-nullable. That's not a default that can be changed, that is the reality of life. There is no way to make a box T, which is Rust's equivalent of unique pointer, null. It cannot be done. Even smart pointers in C++, like unique pointer, whose usage I recommend, by the way, can be nulled out. So what if you do want to have a nullable pointer in Rust? Rust takes a page out of Haskell's book and finds an option T type, which is either none, the empty value, or some T containing a single T. So a nullable pointer in Rust looks like option box T. As a fun bit of trivia, Rust is guaranteed to compile the option box T pattern down to a single nullable pointer at the assembly level. This is called niche optimization, and it fires when two things are true. First, the inner type, box T in our case, must have an unused bit pattern known to the compiler. Since our pointer is guaranteed non-null, the bit pattern of all zeros representing the null pointer in C is unused. Second, the outer type, option T in our case, must have a variant that contains its inner type and a variant of size 0. If both of these are true, the unused niche in the inner type, the null pointer in our case, gets used as the zero-sized variant of the outer. Thus, adding an option around a smart pointer such as box gives us compile time safety, for an option cannot be accidentally dereferenced before checking the null case, at 0 runtime cost. This is a zero-cost abstraction, a common theme in the design of the Rust programming language. We'll be talking a lot more about Rust in the future, including its reinvention of the notion of a class using Haskell-style sum of product types and type classes, as well as its monadic-style error handling, but for today, let's write some code. We'll build up our program in 3 functions, 2 helpers and a main. Our first helper checks whether a given candidate product and a pair of multiplicands is pan-digital. First, convert all 3 numbers into one long string, so that we can get all the digits. Then iterate over the string, remembering the digits we've seen so far. If we encounter a duplicate digit or fail to encounter a digit, then this is not a pan-digital product. There are a few things worth noting here. Variables in Rust, by default, are immutable, and when I say immutable, I don't mean final in the sense of Java or const in the sense of JavaScript. Both of those keywords merely prevent rebinding the variable, but the contents of the variable, for instance, individual elements of an array or values in a dictionary, can still be mutated. In Rust, all variables, unless explicitly requested, are properly immutable. The concatenated digits variable here is guaranteed to be an immutable string. On the other hand, by using the keyword mute, the ACC variable is a mutable hash set. An understated fact of programming language design is that of what I call Huffman complexity. Programmers will tend to use features that require less typing. In Rust, let is 4 characters shorter than let mute, including the space, which means it's more likely to be used as the default. Conversely, in JavaScript, const is longer than let or var, which means a lot of people will favor the mutable type as a default. Making the immutable path both the default and the shorter alternative encourages the average Rust programmer to minimize mutability, as we do here, but not to outright avoid it as we might try to do in Haskell. As another minor point, Rust is an expression-based language. Similar to Ruby, in Rust, the final expression of a function is implicitly returned, but we can also exit early with the return keyword, both of which we do here. Our second helper function, given a product candidate, identifies whether or not it can be written as a pan-digital product with the correct choice of multiplicands. We're going to iterate over all the possible first multiplicands from 1 up to half the product. Once we've identified A, check if the number indeed divides into the product. If so, identify B, the other multiplicand, and check if it contains all of the digits when written as a product expression. If so, return true. If we reach the end of our loop, default to false. Finally, we write our main function. Create an accumulator variable, then iterate from 1 to 10,000. If the number we're looking at is a pan-digital product, add it to the total. Finally, print the total. This runs instantaneously and gives us our answer. I'm not happy with it. It'll do well for our language of the week in a minute, but it looks like a C programmer came and wrote some imperative-style code in Rust. Rust, like many modern languages, has a powerful streaming API for working with iterable objects. Gone are the days of old-school for loops, replaced by higher-level looping primitives that convey exactly what we want to show. But whereas Java and C++ suffer the disadvantage of having to tack on high-level iterable APIs to an existing language that didn't have them, Rust has the distinct advantage that it baked these features in right from the start, resulting in a very ergonomic, easy-to-use system. Let me explain with some examples. Instead of mutating a hash set to check for all digits, let's reconsider the problem from a declarative perspective. I want to know if every digit appears exactly once. Stated more declaratively, I want to know if the sorted multiset of digits in my product expression is equal to the specific sorted multiset 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's exactly what this Rust code does. Create the string, same as before, then accumulate the characters into a vector, sort that vector, and see if it's equal to the one we expect. Let's give our second helper function the same treatment. This is where we'll really start to see the benefits of the streaming API. This function endeavors to ask the question, given a product, is there any pair of multiplicands such that the contains all digits function is satisfied? Right now, the declarative explanation is not readily apparent from the implementation, so let's try again. Calculate the upper bound, then iterate from 1 up to the upper bound. Remove any values that do not divide evenly into the product. Then ask the question, do any of the remaining values satisfy our predicate? Notably, neither of these new implementations use early returns. Both of them read strictly from top to bottom. Finally, our main function can be rewritten similarly. Take all of the candidate values, filter down only to the ones that are in fact pan-digital products per our helper function, then sum the result and print it. This new program is much more idiomatic Rust code than the previous, and I would argue is much more readable as well. Each function to a Rust programmer will be more apparent in its purpose. But we didn't come here to write Rust code, at least not until problem number 54. We're here to write code in lesser-known programming languages. So it's time to go in some sense, the opposite direction from Rust. Rust is a very new programming language, and today we're going to write our code in one of the oldest mainstream programming languages still used today. That's right, it's time to write Project Euler in COBOL. COBOL came out in 1960, and in many ways, it's the Java before Java happened. Today, we think of Java as the stable, idiot-proof enterprise language, used at big companies that prioritize compliance and stability over productivity or developer ergonomics. COBOL was the original language to set those priorities forth. COBOL is still used today, mainly in the banking or financial sectors, where regulatory compliance and absolute numerical precision are paramount. I suspect most people watching this video have at least heard of COBOL, probably as the butt of some joke about old gray-haired developers or the like. But the legacy of COBOL as a language should not be understated. For instance, COBOL was the first programming language designed explicitly to run on multiple vendors' hardware. We think of the mantra write once, run anywhere coming from Java with its jar files, or before that we think of it coming from C with its single syntax compiling down to a variety of assembly dialects. But C came out in 1972. COBOL did it first. Similarly, COBOL widened the scope of programming in general. In the 1950s, Fortran was the state of the art. Programming was seen as a useful tool for data scientists and engineers to run calculations faster than a human could. The idea of using computers to store complex data, rather than just act as a glorified calculator, largely came about as a result of COBOL, with its ability to easily define complex record types. This is a small snippet modified from a James Madison University example. This doesn't look exciting. To a modern programmer in the year 2026, it's just a couple of structures. Every language has it, but I cannot understate how insane this was at the time. A computer storing complex data that carries semantic meaning beyond the mere sum of its bits. COBOL gave us that. And finally, I think this is the part most people are likely to already know, but COBOL made fixed-point arithmetic well known. While the IEEE standard on floating-point numbers wouldn't be out for a few more years after COBOL was invented, the concept of floating-point numbers was already well known. To a scientist, the idea of having a data type that could represent numbers of vastly varying magnitude makes perfect sense. We're just applying the high school rules for significant figures, but encoded in base 2 and done automatically on a computer. But COBOL wasn't targeting scientists, and thus eschewed this notion in favor of fixed-point arithmetic. In COBOL, a number has fixed precision after the decimal point without a magnitude multiplier. This makes it more suited to financial applications, where the loss of precision from large floating-point numbers would cause problems in practice. Fixed precision arithmetic hasn't become mainstream, but many modern programming languages provide it as an option. Python has the decimal.decimal class, Rust has multiple big decimal crates, and C++ has boost multi-precision. So with all that in mind, let's get started. We'll be using the GNU COBOL compiler as a modern, stable, and ergonomic COBOL compiler. A COBOL program at the top level is split into multiple divisions, similar to the code and data sections of an assembly program. The identification division comes first, which specifies the program metadata. In our case, that's just the name of the program. The second division would be the environment division, which specifies requirements of the source or object computers, as well as information about external resources, such as files required of the program. In our case, we have no such requirements, so we omit that section entirely. Third, we have the data division, which contains all of our global variables. There are other things that can go in the data division, but we can keep it simple in our case. The pic keyword stands for picture, and specifies the storage layout for a given name. For instance, most of our integer variables are declared to be unsigned integers whose maximum value is 99,999. That is, unsigned variables of at most 5 digits. The variables whose picture starts with X are what we would call strings in the modern sense, though they don't follow the C-style convention of ending in null characters, and are instead simply of fixed length. So string 0, string 1, and string 2 are strings of fixed length 6, while string C, the concatenated string, is of fixed length 20. Similarly, temp_s is a string variable of length 1, which will be used when scanning individual characters. As a side note, you'll notice that my editor Emacs is warning us about something here with the orange prefixes. We can safely ignore that. In Legacy COBOL, way back in the day, the first 6 columns of each line had to be left blank, as they were used for other purposes on punch cards. Modern COBOL implementations, including GNU COBOL, do not have this restriction, on account of the fact that we are not using punch cards. Emacs is simply warning us that our code may fail if run on a COBOL compiler from over 50 years ago. Finally, the procedure division contains our code. Our code will look mostly like the imperative Rust solution we wrote first, but we'll factor it all into a single main block for simplicity's sake. Store the sum total in accumulator, which starts at 0. Iterate for counter from 1 to 9,999. Inside, iterate candidate multiplicands from 1 up to the upper bound of counter, divided by 2. If the candidate divides into the counter, calculate the second multiplicand, then stringify all 3 numbers. Notably, we don't have to explicitly convert from an integer to a string here. COBOL understands that moving the variable candidate of picture 99,999 to the variable string 0 of picture x6 should simply work the way we expect. Once we have our 3 strings, concatenate them into string C. Now, rather than inventing a hash set here, we're just going to count the number of occurrences of each individual digit. It's a bit slower in principle, but much simpler. For each digit from 1 to 8, count the number of times we see that digit in string C. If the total count is not 1, then we've failed. Finally, do the same thing for 9. You may wonder why I wrote the code twice, once for 1 to 8 and once for 9. I declared the variable temp to be a 1-digit variable, so if my loop ran from 1 to 9, then the loop would stop when temp is greater than 9. But temp, being a 1-digit number, can never be greater than 9. Hence, run the loop from 1 to 8, stopping at the extremely representable 9, then do the 9 case separately. At the end, if we haven't failed, add the current product value to the sum total and break out of the loop. Finally, display the final total. This runs instantly and solves Project Euler problem number 32 in COBOL. Tune in next time when we solve problem number 33 in XSLT, the XML style language. See you guys then.